Thanks for the introduction. So good afternoon, everyone. I'm Jian Huang. I just graduated from Georgia Tech, so I'm going to join UIUC as the assistant professor. So today I'm going to present our work FlashGuard, which leverages the intrinsic flash properties to defend against the encrypting ransomware. And this work was in collaboration with Jin Xu and Professor Xun Yixin, Professor Peng Liu from Penn State, and my advisor, Professor Moin Kresh from Georgia Tech. So when we talk about the encrypting ransomware, I think everybody still remembers the WannaCry ransomware attack happened on May 12th, and 1 week before the CCS submission deadline in this year. And the WannaCry ransomware attack quickly compromised more than 230,000 computers across more than 150 countries. And for each attack, it asked about $300 to $600, and it generated massive global damages to our data. So what's encrypting ransomware? So normally, our encrypting ransomware will read our files, encrypt the files, and try every means to destroy the original files, and then pop up the screen to ask the users for the payment to decrypt the files. And here, I'm going to use the WannaCry encrypting ransomware as an example to show a few interesting things. So the first thing is that the ransomware will pop up the screen and tell the users that the important files in the computer has been encrypted. And this somehow matches with the previous studies that the encrypting ransomware mainly target the small and the important files on our computers because they wanted to get the ransom as quickly as possible. And another interesting point is that the encrypting ransomware will tell the users how they can recover the files. And they tell the users that they can guarantee their files can be decrypted if they pay the ransom. And they even show a decrypt button to allow the users to decrypt a few files to prove that they can be trusted because they do not want to lose their credibility. And another interesting point is that they show the deadlines for the payment. So if the users delay the payment and they have to pay more money, and if the users don't pay the ransom and the ransomware is going to destroy the encrypted files. And this also shows that the encrypting ransomware wants to get the ransom quickly. So to further understand the encrypting ransomware, we conducted a study on a set of more than 1,400 encrypting ransomware samples. And we categorized these ransomware samples into 30 families. And we wanted to first understand how long it will take for ransom to finish the attack. So we ran the ransomware samples in the virtual machines and measured the time since the ransom started to encrypt the files until they pop up the screen. And as we can see, most of the ransomware will finish the attack in 75 minutes. And this provided evidence to show that the encrypting ransomware wants to get a ransom quickly. And another thing we wanted to understand is that whether the encrypting ransomware is going to destroy the data backups. And as we can see, most of the ransomware is going to do that. And some of the ransomware even try to bypass the user access control and get the kernel privileges to do that. So to defend against the encrypting ransomware, there are a few types of solutions have been proposed. The first one is the malware detection. So for the malware detection, they are going to analyze the data access patterns of the encrypting ransomware and track the function calls in the file system and the encryption library. And the previous work has demonstrated that the encrypting ransomware can be successfully detected when ransomware encrypt 10 files on average. But for this solution, the problem is that even the encrypting ransomware can be detected, the damage has already happened. And another solution is that we can rely on the journaling and the log structure file system, which have been used in computer systems for decades. And as we just discussed, the encrypting ransomware can get the kernel privilege, so it's easy for them to destroy the logs. And also, we can rely on the networks and the cloud storage to do the data backups. But for this solution, the problem is that this will not only increase the storage cost, but also decrease the storage performance. And most importantly, the encrypting ransomware can get the kernel privileges to stop the cloud services. So in a summary, the existing software-based solutions are not good enough to defend against the encrypting ransomware. So we really need to think about the survival models of the encrypting ransomware. The ransomware can get the kernel privilege, so it's easy for them to not only destroy the user space programmers, but also compromise the operating system. So in our work, we don't think the operating system can be trusted. In this case, it's natural to rely on the hardware to solve this problem. So in this project, Our goal is to defend against the encryption ransomware without rely on software-based solution and also without explicit data backups. So when we take a deeper look at the hardware device, and there's a trend that we cannot ignore is that the flash-based SSD has been widely used to replace the hard disk drive. And this is because the flash-based SSD performs much better than hard disk drive, and also their cost is keeping dropping. And also the flash-based SSD is fundamentally different from a hard disk drive. And more specifically, the flash-based SSD has no mechanical cycle operations, so it provides much lower latency than hard disk drive. And also for today's SSD, they have already packed dozens of parallel chips to provide increased parallelism to satisfy applications requirement on throughput. And also the price of the flash is keeping dropping. So for example, for today's flash device, it only costs $0.2 per gigabyte. So over the last decade, we have seen significant improvement on flash. And because of these advantages, flash has been widely used in our laptop, desktop, servers, and mobile devices, and even wearable devices. And even though the flash is used on different platforms, but the way how it is used is pretty much the same as the traditional hard disk drive. So flash is used as disk. Applications interact with the file system to access the data on the flash-based disk. The only difference is that the flash-based SSD has a flash translation layer, and the flash translation layer was designed specifically for flash. And it has one major function called auto-place update. And this is because every time when we overwrite our flash block, we have to erase the block first. But the erase operation is quite expensive. So instead of erase the flash block every time, and we just write the data to a new block. And then because the address has been changed, and we maintain the mapping address in the flash translation layer. And then later on, we run the garbage collection to collect the invalid data in the SSD. So in FlashGuard, we leverage the intrinsic flash properties to defend against the encryption ransomware. And instead of trusting the operating system, and we trust the SSD firmware, and this is because of two reasons. The first one is that the SSD firmware is implemented in the flash kernel, and which is hardware isolated to the ransomware processes. And the second, compared with the OS kernel, the flash firmware has a much smaller trusted computing base, so which means that it's less vulnerable to malware attacks. So by leveraging the intrinsic flash properties, we can retain the data in SSDs without hardware modifications. So for example, when we overwrite our block, and the SSD is going to write the data to a new flash block and change the mapping address in the flash translation layer and mark the older copies as invalid pages. And the garbage collection is going to garbage collect it later. And this is fundamentally different from the traditional hard disk drive. So when we overwrite our block, the hard disk drive is going to physically overwrite the data. So, but the challenge here is that if we retain all the invalid pages in SSD, and this will be very expensive, it's because the storage capacity is limited, and this will increase the GC overhead. So it's important to retain only the invalid pages caused by encryption ransomware. But the challenge here is that the flash kernel has low information about the application semantics. It has low knowledge of which pages should be retained or not. So when we take a deeper look at the ransomware patterns, and there are two categories. The first one is that the encryption ransomware is going to read the files, encrypt the data, and overwrite the original files. And another pattern is that the encryption ransomware read the files, encrypt the data, and encrypt the data to new files, and try every means to delete and overwrite the original files. So in either case, the ransomware is going to read the files and overwrite the original files. And based on this observation, and the key idea of the FlashGuard is that we only retain the invalid pages that have been read for a certain period of time. And we may wonder that the regular storage operations may generate the similar data access patterns like the encryption ransomware, such as the data compression. But this is not a concern in practice because for this type of storage operations, and they only occupy a small portion of the storage operations for a long time. So for example, we collect the storage traces from the university computers over 20 days, and collect the storage traces from the enterprise servers over 6 to 10 days. And as we can see, the read-overwrite storage operations only occupy a small portion of the storage operations over a long period of time. And also, the size of the invalid the invalid page caused by the read overwrite storage operations is very small, and it's only a few gigabytes. So it's much smaller than today's storage capacity, which has terabytes. So far we discussed how we retain the data in SSDs. Now let's discuss how can we tracking the invalid data in SSDs for future data recovery. So here we leverage the metadata to do that. So for each flash page, it has 16 to 64 bytes out-of-band metadata. And this out-of-band metadata can be used to store any information we want to store. And in FlashGuard, we use 4 bytes to store the logical page address that mapped to this physical page. And we use another 4 bytes to store the previous physical page address that mapped to the same logical page address. So in this case, it's easy for us to recover all the invalid pages that mapped to the same logical page. And we use another 4 bytes to store the timestamp to track how long this page has been retained in the SSD. And we use another bit to indicate whether this page is a retained invalid page or not. And we also slightly modify the garbage collection to make sure the garbage collection in SSD is not going to erase the retained invalid pages. So when the number of free blocks in SSDs is under the threshold, the garbage collection will be triggered. And they are going to collect the invalid pages, compact the flash block, and so we have enough free blocks for future storage operations. And here, the FlashGuard leverages the existing greedy algorithms to select the flash blocks, which means that we always select the flash block which has the least number of valid pages. And it's noted that in FlashGuard, we treat the retained invalid pages as valid pages. So this can delay the garbage collection for the flash blocks which have the retained invalid pages. So for example, in traditional SSD, and the block C is going to be selected as the garbage collection candidate. This is because the number of valid pages is the smallest. But in our solution, the block A will be selected. So the flash block which has the retained invalid pages will be delayed. So once the flash block is selected, and we are going to copy the valid and the retained invalid pages to our new block, and change the mapping address in the flash translation layer. And then we are going to erase all the flash block. So now let's discuss how can we do the data recovery with the FlashGuard. So as we discussed, each flash page has 16 to 64 out-of-band metadata, and we leverage this metadata to retrieve the index information for data recovery. And so once the encryption ransomware is detected, and we plug out SSD and plug it into an isolated and a new environment, so in case the ransomware is going to attack our recovery procedure. But here, there are still 2 challenges. The first one is that we need to locate the invalid pages in SSD. And a simple way to do this is that we check the flash block one by one. But for 1 terabyte SSD, it has millions of flash blocks, which will take a very long time. And another challenge is that for each logical page, it may be overwritten by many times, which means that it has many invalid pages. And also, there are lots of invalid pages in SSD. So it's challenging to build the logical connections between these invalid pages in SSD. So to overcome the first challenge, we leverage the internal parallelism SSDs to accelerate the data recovery procedure. So we leverage the parallel chips in SSD to parallelize the data recovery. And to overcome the second challenge, we leverage the previous physical page address metadata stored in the out-of-band metadata. So the previous physical page address is used to track the invalid pages that are mapped to the same logical page. So once we have this information, it's easy for us to recover all the invalid pages that are mapped to the same logical page. And also, in the out-of-band metadata, we have the timestamp and also the logical page address. So it's easy for us to sort the invalid pages with the timestamp. So we implemented the FlashGuard with the programmer SSD with the capacity of 1 terabyte. And for each flash block, it has 64 pages. Each page has 4 KB. And in FlashGuard, we set our provisional ratio to be 50% by default. And to test whether the FlashGuard can recover the data once the SSD is attacked by the encryption ransomware, and we use the more than 1,400 encryption ransomware samples to do that. And to evaluate the performance of the FlashGuard, we use 4 types of storage workloads. The first one is the storage traces collected from the enterprise servers. It has 11 workloads. And another set is from the university machines, which has 6 workloads. And we also use the storage benchmarks like the IO zone and the postmark to evaluate the performance of FlashGuard. And we also run the database workload like the TPCC and the TPCE to evaluate the performance of FlashGuard. Now let's first take a look at the recovery time of the ransomware samples. So when we run 13 families, and we can see the victim data size is about 4 GB. And for this victim data, the FlashGuard can recover the data in less than 1 minute. And this is because we leverage the internal parallelisms of the SSD to accelerate the data recovery procedure. And it's noted that the recovery time is not proportional to the victim data size because the invalid pages are not evenly distributed across the parallel chips in SSD. Now let's take a look at how the FlashGuard will affect the regular storage operations. So as we can see, the FlashGuard decreased the storage performance by up to 6% for IO-intensive workloads. And this is because of 2 reasons. The first one is that the size of the retained invalid pages is small. And the second is that the FlashGuard will delay the garbage collection for the flash block, which have the retained invalid pages. Now let's take a look at how the FlashGuard will affect the SSD lifetime. And to evaluate the SSD lifetime, we use the write amplification factor as the matrix. And the write amplification factor represents the actual write traffic, the ratio of the actual write traffic to the logical write traffic. So as we can see, the FlashGuard increased the write amplification factor by 4%. And this is mainly due to the additional page movement in garbage collection. And this is also lesser concern in practice because normally our SSD would last 3 to 5 years. If we decrease the lifetime for 1 week, and this is fully acceptable in practice. So when we develop our solution to defend against the encryption ransomware, the ransomware will also develop to attack us. So for example, the ransomware can leverage the garbage collection characteristics in SSDs to attack us. And they can keep writing data to the SSD to trigger the garbage collection frequently. And for this case, the FlashGuard will retain the data until they become expired. So when the SSD is full, and they are going to stop issue any IO request, and this will cause the failures of the file system operations. And for this case, it's easier for users to observe the abnormal event. And another potential attack is the timing attack. So the encryption ransomware may make the attack last for a longer time. And as we discussed, and the encryption ransomware wants to get the ransom as quickly as possible. So if they make the attack last for a longer time, and it's easier for them to be caught. And this will increase the chance to be caught. And FlashGuard is also compatible with the security deletion. So which means that when the users delete the file, and we should make sure the deleted files are not going to expose to anyone. And this problem has been solved in previous work, and the FlashGuard is going to integrate this work in the future. So let me summarize our FlashGuard work, and we propose a hardware-assisted defense solution against the encryption ransomware by leveraging the intrinsic flash properties. And it has minimum impact on the SSD lifetime and performance. And thank you very much. I'm happy to take your questions.
Please say your name and affiliation.
Yeah, Xiangning Li from Alibaba Cloud. So thanks for awesome talk. So I have a question here. First thing is, what's the vendor or the flash vendor you are using for programming the firmware to implement your feature?
Okay, so we are using the OpenSSD.
Oh, OpenSSD.
Yes.
So you can.
We can modify the firmware.
Oh, I see. I see. Okay. So because I think you mentioned the garbage collection part is the problem because that will impact the life cycle for the whole SSD, right?
Yes.
So do you think you have some better solution to solve this kind of problem? Because I still think if attack can trigger this kind of thing and you overwrite too much time and the life cycle will be impacted.
So actually for this kind of attack, it's easier for users to observe the event because when there are lots of garbages in the SSD, the regular storage operations performance will be dropped eventually, right? It gradually will drop. So when as a user, you will observe that, okay, my application's performance is keeping dropping. So you may wonder that there's some abnormal event happening in my computer. So it's easier for users to identify this kind of attack.
Okay, thank you.
Fengwei Zhang from Wayne State University. So, very cool talk. I'm just in the beginning you mentioned you have ransomware got some of the statistics to saying that some of ransomware even get into the kernel breach. So I'm just wondering, do you have any data for that to like say how much % of ransomware will have the ones to get the kernel breach?
We don't have a concrete number. I think more than half, 6%, 70% of the ransomware is going to get the kernel privileges. So we run the ransomware in the virtual machine and try to give the permissions to see if they are going to delete the data backups. And we find that most of them is going to do that. Yeah.
Thank you for your talk. My name is John Podolenko from University of Texas at Arlington. I'm actually doing a little bit of ransomware research myself, and one of the things that I've noticed is that a lot of research involves people doing just like a very basic install of Windows with maybe a few additional files. So you're talking about maybe 4 gigs of files were encrypted, but what happens when somebody even has a solid state with, let's say, 940 gigs used? For example, my Mac over there has a terabyte, and I'm using about 940 myself. So what happens when somebody has a nearly full hard drive or solid state drive? Is this gonna still, how would that affect your approach?
So your question is that if people use the hard disk drive?
No, I meant solid state drive. I'm sorry, I said hard drive. But my question is if somebody has a much more full solid state drive at say 80-90% capacity, how is that going to affect your approach?
Okay, so you mean the capacity, the remaining capacity can be used in the SSD is small, right? Is that your question? So how this will affect our solution, right?
Yes.
So for this case, even though we don't have much space remaining, and once we find that this invalid page is potentially caused by the encryption ransomware, and we will retain the invalid pages in SSD until the SSD is becoming full.
Okay, and then if it's still, let's say
we are still
anyway,
we are going to retain the invalid pages in SSD. Yeah.
Okay.
Hi, Kevin Butler, University of Florida. Do you deal with, so a lot of these SSDs, the Samsung SSDs, et cetera, have Opal and they have full drive encryption already on there. So how do you address the FDE issue if you're looking at data that's already encrypted? Is it because you're acting at the FTL that you're doing the comparison there before encryption happens? What's the relationship between data that's encrypted at rest on the disk and the ransomware or activity that looks like ransomware? So
the question is about if the encryption, right? So that the data is fully encrypted. The encrypt the file system, right?
Right, or even the disk itself providing encryption. Or if I want to turn on FDE on a drive so that everything is encrypted in the first place, then
so for that case with so this will increase the performance overhead. But anyway, so even for the encryption of file system, and we are still going to if we find that the data is read and overwrite again, and we are going to retain these invalid pages, no matter whether this is whether the file system is encrypted or not, and we are going to retain the invalid pages. But the problem with this solution is that this will decrease the storage performance.
Let's thank our speaker once more.